Hello, my name is Fabio Pizzati and I am going to present our work on model-based occlusion disentanglement for image-to-image translation. In this work, we tackle a problem occurring in image-to-image translation, which consists in learning a transformation between a source and a target dataset, in order to apply to the context of source images the style of target ones. For example, it is possible to make synthetic scenes look more realistic, as in the top figure, or to apply different adverse weather conditions to clear weather images, as here from a clear weather scene to a snowy one. Generally, the transformation is learned by GANs in an unsupervised manner, and it could require paired images, which represent the same scene in both source and target domain, or unpaired ones. We will talk about unpaired methods since it could be challenging to collect paired datasets. There are cases in which state-of-the-art networks tend to fail. This is a result of a state-of-the-art network translating from clear weather images to rainy ones that has been trained on the multimodal new scenes dataset for autonomous driving. As you can see, even though many typical aspects of rainy scenarios are correctly generated, such as reflections on the asphalt, there is a strong presence of gray artifacts in the upper part of the image, which impacts the image realism. Furthermore, these artifacts are way more evident on certain elements, such as trees and buildings. We advocate that those artifacts are the learned representation of raindrops. In this example, you can see three scenarios of target domains that cause issues similar to the ones shown before, and all encompass occlusions. The elements circled in red in the image at left are out-of-focus raindrops, while in the center one there is an evident soiling occlusion. In the right image, a watermark has been applied that behaves as an occlusion since it is independent from the geometry of the scene. In the previous video example, the GAN is trying to simulate the appearance of raindrops adding the artifacts shown before. But having no knowledge of what occlusions are, the GAN will treat them as they were effectively part of the recorded scene. At the end, what is learned is an entangled representation of occlusions and scene that impacts image realism. A way to solve this would be guiding the GAN learning in order to disentangle the representation of occlusions. As an additional constraint, this is impractical to supervise, since occlusions may be extremely challenging to annotate. With semi-transparent occlusions, for example, it is also difficult to define what is occluded and what is not, as here with raindrops. To solve the problem, we propose a physics-driven strategy to learn scene and occlusions disentangled representation in an unsupervised manner. The core idea is to learn the scene representation with the GAN, while the occlusions one with physical models with learnable parameters. The resulting images will consist in a blending of translated scene and occlusions. We tested our method with 4 different occlusion models, but I'm going to focus on raindrops since they are quite challenging for their refractive and semi-transparent appearance. An evident benefit of extracting a disentangled representation would be the possibility of re-injecting occlusions with different physical parameters with respect to the ones in the target dataset. Talking about raindrops, once the scene representation is learned, we would be able to use the physical model to re-inject, for example, unfocused raindrops like those of the target dataset, or different ones, and obtain images like the one at the bottom which resemble a dashcam collected image. This would be extremely important for improving performances of algorithms in bad weather with arbitrary camera setups. Here it is represented the standard architecture of a GAN, where a discriminator is trained to distinguish between real images and fake ones, so generated by the generator. The generator is instead optimized to fool the discriminator. Being image-to-image translation, the generation is conditioned on the source image. Dashed arrow represent the gradient flowing. It is well known that GANs are probability distributions estimators, so at the end the task of the generator would be to estimate the target probability distribution. We define as Px the probability distribution of source data and Py the one of target. Our intuition is that the target distribution is a joint probability distribution encompassing both scene and occlusions random variables. But for their nature, occlusions are fairly independent from the recorded scene, so it is possible to use the independency properties to separate the two marginals. Knowing one of the marginals, it would be possible for the GAN to learn the other. So we assume to know which kind of occlusion is in the target dataset, so in the example raindrops, and we assume to model it with physical models. In practice, what we do is to inject occlusions with the physical model on generated images before forwarding them to the discriminator. So it won't be needed anymore for the generator to generate raindrops to fool the discriminator, and Gx will just approximate the marginal relative to the scene, here Pys. In reality, there may be little dependency between scene and transparent occlusions, but we evaluated in the experiment that this is not sufficient to hurt disentanglement. Logically, the occlusions models should be as similar as possible to the ones in the target dataset. For this reason, we designed a method to regress the optimal parameters of the physical model, omega tilde, which represent the physical nature of target dataset occlusions. To do that, we train a naive eye-to-eye GAN in an entangled manner and extract a pre-trained discriminator D-end. We then freeze the discriminator and use it to optimize the physical parameters of our model. What we do is injecting occlusions in the images of the source domain and backpropagate the GAN loss. The optimization process will lead to reducing the differences between source and target domain, but just modifying the occlusion's appearance. Using this process, we reach an optimum in correspondence of a set of parameters omega tilde, which renders occlusions resembling target ones, and that we use in the training routine previously presented. Here the full pipeline is shown, where in addition to what already introduced there is noise, regulating random characteristics of occlusions such as shape or position, and the disentanglement guidance, which is a learned component used to guide the network on where to reinject occlusions. To understand the intuition behind the disentanglement guidance, let's consider a transformation from clear weather to rainy and look at the ground truth data. As you can see, there are very visible differences between some parts of the scene, such as the asphalt, which varies greatly between the two domains. Instead, there are regions which do not vary much visually, as here with trees. Our idea is that learning to model regions with lower domain shift, so which vary less, will be harder for the GAN, because even assuming a perfect transformation, the visual differences are not so significant. Hence, it could be more convenient for the generator to entangle occlusions there, since they are present only in the target dataset and so they are a strong discriminative signal for the target domain, and a fast and easy way to lower the domain shift. For this reason, we design our disentanglement guidance estimation, which consists in averaging the gradient feedback of the pre-trained discriminator layers over all the source dataset. This returns an estimation of the domain shift in the source dataset. We threshold the guidance to obtain a mask that we use to inject synthetic occlusions only on low domain shift areas. For raindrops disentanglement, we use a simple physical model based on refraction. A drop is simply encoded as a displacement color map, and a constant thickness value is used as a multiplier for the displacement values on both axes. Noise is regulating shape and position, while at the end we apply a defocus blur kernel in order to simulate unfocused raindrop appearance. The variance of that kernel is the parameter we are trying to regress with our adversarial strategy. We specifically regress defocus blur parameters because different blur kernels could drastically change the rendered raindrop appearance. Here are presented some results on clear weather to rain transformation. As you can see, our baseline, which is munit, tend to partially entangle drops on the top of the tree, but also the image is generally blurry. Instead, we are able to recreate better target image drops with the estimated omega tilde, so with the parameters learned from the target dataset. Our method is able to extract a disentangled representation without drops, which appears of higher quality. Please note that this representation has been learned without having seen images without raindrops and without any supervision. Also, as I introduced before, we can also render rainy scenarios with different parameters, as here we choose dashcam-like styles. The backbone network we use is always munit, so our method could be integrated in any GAN baseline. I'm briefly presenting also a quantitative evaluation against 5 baselines or metrics which quantify image quality and diversity. It is evident that extracting disentangled representation of the target style is beneficial since we rank first in all 3. Note that SciIS is just evaluated for multimodal methods since it quantifies multimodal variability. Our method also enables to control occlusions, so we can define complex motion behaviors to increase video realism. Here, for example, we show 2 translated videos with moving and focused raindrops. Please note that we do not explicitly enforce video consistency on the underlying scene. We studied the effectiveness of disentanglement guidance varying the threshold we use to obtain the binary mask. For a threshold to 0, we fall back in the baseline scenario, so we obtain entanglement. For threshold too high, so injection of occlusion also in high domain shift areas, we achieve disentanglement, but we lose some of the translation capabilities of the network. Look for example to the asphalt that has no reflections. Only a correct sizing of the threshold leads to a disentangled and realistic transformation. In our experiments, we also tested the method on both soiling occlusions on the woodscape dataset and synthetic occlusions as watermarks and fence-like grids on Cynthia from clear weather to snow. Since there is no domain shift in woodscape, we use as source images grayscale ones, so again we also need to learn colorization in an unpaired manner. The baseline unit, as expected, entangles scene and occlusions and gives unrealistic results. Our method is instead able to learn the style transformation regardless of occlusions. Finally, we also quantified the effectiveness of our parameter estimation strategy on the robot car dataset, which have couples of paired images collected with a stereo pair, where one camera is clean and the other is wet by a specific setup. In a very recent paper, they render raindrops with high realism on clear weather images using a physical model that is very similar to ours. But our results, thanks especially to the defocus blur estimation, is way more similar to real images with raindrops. We demonstrated the usefulness of model-based occlusion disentanglement for image-to-image translation tasks. In the paper we include additional experiments such as quantitative evaluation for other occlusion types, usability for segmentation in adverse weather, and additional ablation studies. Thanks for your attention, and if you have questions, I'll be happy to answer at the Zoom sessions.